Welcome to Making IoT. Today we are going to look at the Airwick. The Airwick is a device that sprays some aerosols at fixed intervals to, as the packaging says, give continuous freshness for up to 60 days. We will hook into the device so we can control it remotely. We want to be able to change the intervals to settings that aren't supported by default, and we also want to be able to trigger a spray remotely. So this is now the end of the unboxing part. As next step, we want to understand the functioning of the device. So this white thingy here is the main unit, the main part of the Airwick. It drives everything. We're going to add some batteries and then trigger it, which will start a timer, and after a few seconds we'll push this red button in the center up, which then pushes on the spray bottle. Important here, we can see there's a diode, and this diode means that we can actually turn the motor back without damaging the electronics. We're looking at the board now. The battery is connected to the big pins at the bottom. The positive one is on the right, and the negative is on the left. The positive pin has a trace that goes up on the left side to the motor. This is what we are testing now. So there's a direct connection from the positive pin to the motor. For the negative pin, we are testing now where it is connected to, and it is connected directly to the switch. So the switch completely disconnects the negative side of the battery when the device is turned off. Next, we want to see how the motor is turned on and off. The red probe is currently touching the transistor that is responsible for that, and there's the base of the transistor is connected to a resistor, which is touched now by the red probe, and then from there it goes to the top left pin of the integrated circuit. It's now time to connect some wires to the board. The first one is the positive, the red wire on the same pin as the motor. Had a little bit of trouble heating it up. And even after it was hot, still wasn't great. So I tried again, warmed it up again, and then I was happy enough with it. Second pin is the pin that connects to the base of the transistor. Not a great joint, but good enough. And finally we are connecting the ground, the negative pin. There we have lots of space and two pins that we can connect from the switch. So this one is definitely an easy one. It's time to measure how the Airwick's microcontroller is driving the transistor. I have an ESP32 dev board on the right side, and I'm connecting the red and black cable to power and ground. And I have also an additional white cable which I soldered directly to the pin that drives the transistor. We're using Toit.io as development platform. It already starts with a hello world, so we might as well just run it. We get a response back, which is good. The ESP32 is online and working. Now we want to see what the Airwick controller actually does. So as a first step, we are going to look at the white pin which is connected to the controller directly and see what it emits. So we have connected that cable to pin 18, and we are setting that pin to input and just print what we get from that pin. unsurprisingly we get 0, so it's basically to ground, and the base, the transistor, is therefore not letting anything through. As a next step, we want to know for how long the controller, the Airwick controller, keeps that pin to 1 when it enables the motor. So we first wait for the pin to go high, we take the time, and then we wait for the pin to go down again, and after that we just print the difference time. So now we also need to enable the Airwick controller, so we change the switch to on. Now we have to wait for the controller to do the first activation of the spray. That takes a little bit of time, but once it starts, we will see, and now we see the 700 milliseconds that the Airwick controller keeps that pin high. We now have everything to simulate the Airwick controller ourselves, so we disconnect the white cable that we just used to measure and put the yellow cable instead. However, since we soldered the yellow cable after the resistor, we have to introduce the same resistor ourselves. So that's what I'm doing right now. And then we can connect the yellow cable just after in series to the resistor. Once that's done, we can now go back to coding and start by switching the pin 18 to output. Fundamentally, we want to drive the transistor ourselves now. We just set the pin to 1, and then, as we measured before, we need to wait for 700 milliseconds so that the motor can do its job. And after that, we just set the pin back to 0. And it's a success, so we can now move on to create an ESP32 that fits into the Airwick. So we can't use a dev port, that would be way too big, so we are just using a room module as seen here, and now we need to plug it into a programmer so we can provision it for the first time. And these modules, they're not just smaller, they're also much cheaper, so once you have this programmer, it's nicer to just buy small few modules and program them as needed. With again, we are using the TOID platform, so we are now provisioning the device. This only needs to be done once at the very beginning. Once it's provisioned, we can always update the software over the air. So this is a one-time thing, which is kind of convenient for us because we are going to keep the ESP32 inside the Airwick and don't want to ever take it out. More importantly, as we will see in a little bit later, we also want to solder onto the module, and once we have soldered onto the module, it's kind of hard to attach the pins again to program it through wires. The provisioning gives us a URL for the device, and we are going to check if the device is actually working and comes online. It's online, so we just run the small hello world to really do a smoke test and see if the ESP works. So the hello world worked, so now we can take it out and solder onto it. We are going to solder directly onto the ESP32 without any additional controllers or chips. We are using the pin 18 as we have written in the code before, and we also need to set power. We also need to put 3.3 volts onto the input of the ESP32. Note that we short circuit the 3.3 volt and the enable pin. We we always want to have the chip enabled so we can just short circuit those. And then there are multiple ground pins on the ESP32, but we are just going to use the big one in the center. So we are connecting now the wires, the ground first. Then the 3.3 volt. And last, the IO18. But for the IO18, it's important to remember that we still need to put the resistor there. So instead of soldering the wire, we just put the resistor directly, and we will insulate it a little bit later. That was one of the easiest soldering I had. Now we want to test the ESP32, the soldered one, so we don't actually use the dev port here. The only thing we do, we use the 3.3 volt from the dev port here, and then otherwise connect directly to the Airwick port from the new ESP32. So by powering up the dev port, we provide power to the ESP32 and also the Airwick port. We wait a little bit to get it so it comes online. Once it's green, it means it's online. We do again a smoke test with Hello World. It's still running, it's still working, so we didn't fry it. Copy paste the old code of running the motor, and as before, it still works, so we are for one happy, and also we can proceed to the next step. We're now going to connect the ESP32 to the Airwick board. I have cut off the wires, and we are now connecting them directly to the board. There are 3 wires. That's the power, the red 3.3 volts, the ground, black, and the yellow, which goes to the pin 18 to drive which goes directly to the base of the transistor. This is now a good time to talk about the connecting the power of the ESP directly to the board of to the power of the Airwick board. The Airwick board just has 2 batteries there, which is roughly 3 volts. So we are not using any intermediate chip, and that has a few consequences. One is that it's not regulated, but batteries are generally relatively good for the board. But more importantly, it will not be able to drain the whole batteries. So the cutoff for the ESP32 is higher than the voltage of empty batteries. So we will have to change the batteries a little bit earlier than necessary, more or less halfway through. And we will also get batteries out that are not completely drained. It's just so much easier this way that we don't care too much. We're now using shrink wrap to insulate the wires and make sure there are no short circuits. And then apply a little bit of heat to make sure they don't move. To make sure that the cables don't move too much and break out, the wires are not best quality, and neither are the soldering connections. I'm using a hot glue gun here. This is really just, it's mostly to make sure that it's a little bit more stable in the device. We are now at the assembly stage. There's a lot of space in the Airwick, so it's not a hugely difficult task. However, the wires come out at places where it's not that easy. It's a little bit finicky, so I'm speeding this up. To be honest, this is also a clip of an assembly where it didn't really work. There was pressure in the wrong places and the gears didn't work correctly, so I had to do it again. But it's just to show that it's not hugely difficult. There's a lot of space in the Airwick. And here we have it, the moment of truth. The Airwick is fully assembled. The switch is on the off position, batteries are in. And now we want to remotely trigger the spray. And there we go, it worked. We are not completely done yet though. What we really want is to control the Airwick through our CLI or through an Flutter app. We don't want to go to the web page all the time. For that, the Toit framework has a pub/sub mechanism. So there are subscriptions that can be subscribed to and sent to through the Toit servers. And here we are creating this subscription. Every subscription that is available through the servers must be prefixed with cloud colon. So here we have a cloud colon Airwick and we just give it a name of spray. It takes a few seconds for subscriptions to appear, but once the subscription is available, we can use it from any program that knows how to talk to the Toit servers. Now we create a project in Visual Studio Code. We have two files, Airwick Toit and airwick.yaml. In both files, we are copying the example code from the Toit documentation. And now we're going to adapt it. So this code here, the YAML code, is the one that is responsible for running the application on the ESP32. So we are creating a new application that is called Airwick. And as entry point, we use the airwick.toit. So the application starts the airwick.toit file. And as a trigger, we said that the program should be launched whenever there's a message on the Cloud Airwick topic. Similarly, inside the airwick.toit, we are starting from the code that comes with the documentation. We are switching to the topic Cloud Airwick, and now we are just reacting to any topic on any message that comes in. We're starting by printing a small message, and then we created a local variable called already sprayed that we set initially to false. And then we handle every message that comes in. And if you already sprayed this time, we just continue in the subscribe method. We just consume all the messages that we are not spraying another time. Otherwise, we set the Boolean local already sprayed to true. And we do the same thing we did before on the web interface. So we create a pin on GPIO pin 18, set it to 1, sleep for 700 milliseconds, and then we set it back to 0, and that's how we spray. With that, the application is done, and we just need to send it onto the ESP32 device. For that, we created the Airwick YAML file, and we just now need to tell the Toit system to upload it to the spray. So I've renamed the ESP32 to Airwick Spray to make it a little bit easier to find. And by clicking on the deploy button, the left button, we can just send the application to the device and it's installed immediately. Now that it's installed, we can send a message to the subscription. Again, we're using the example from the documentation, and the only thing we did, we changed it to our topic. And it worked again. And the only thing we now need to do is change the configuration of the ESP32. By default, it's online all the time, which is just draining the battery way too fast. So we're changing it to 10 minutes. This means that the subscriptions, the messages will potentially take up to 10 minutes before the spray gets them. But for an Airwick, that should be fine. Thanks for watching.